Hello everybody, and welcome to our video on double integrals over rectangles. So now what we want to do is consider a function of two variables that are defined on some closed rectangle. So this model's a little buggy here, but you can see we've got this rectangle in space here on our xy plane. And so the function f of xy is describing like this red surface up here, right? That's above that. Okay. So, in other words, this is the set of points where x is between some a and b, and all the y values are between some c and d. So you'd have x, a here, b here, c here, d here. And that describes your whole rectangular region. What else? We also assume that the value of the function is strictly positive or equal to 0 here. Then the graph of f is a surface with equation z equals f of xy. Let S be the solid that lies above R, above the blue rectangle here, and under the graph of f. So, in other words, the solid with coordinates x, y, and z. Oh, there's a little typo there. So the solid with coordinates x, y, and z, where z is between 0 and f of xy, and xy is the set of all points in the rectangle. Okay, so how can we find the volume of that figure, of what lies beneath that red surface here? How can we find the volume of this? Well, first, we take our region R and we partition it into sub-rectangles by dividing up the intervals AB and CD. So on your x-axis, you take from A to B, cut it up into a bunch of pieces, and so you get these long rectangles here. And then you cut up your interval on your y-axis from C to D. And each of these individual rectangles is what we call a subrectangle. So all we're saying here is we take A and B, and we pick a bunch of points in between A and B to define our subintervals. And we do that for C and D as well on the y-axis. And then each rectangle that we get, we call a subrectangle. So in each rectangle, we choose a sample point, x sub ij star and y sub ij star. And with that sample point, we can approximate the part of S that lies above Rij by a thin rectangular column. So take a look at this picture. Now this one is not a 3D model, just a regular picture here. But if you see, what we've done here is we've taken a curve in three-dimensional space and divided up the region it was laying over into 4 separate pieces. And of those 4 separate pieces, what we did was take each one and make a rectangular prism that approximated the volume under the curve there. So in other words, each rectangle gives us a volume for the rectangular prism that's found by taking the height of the function at that point times the area of that rectangle that it's lying above. And so the whole volume would be approximately the sum of each of these pieces. So the volume is the sum of all the rectangles, first in one direction and then in the other. So hopefully I can make some sense of that. We've got I and J here as our 2 coordinates, right? So you've got rectangles going this way and this way. So for each, let's say y1 here, right? So for y1, I have all of these different rectangles that correspond to x0 through xm. So we get this double sum. So for I equals 1, I've got to take all the rectangles that lie in that first row which is height times the area of the rectangle, right? So when I is 1, I go across all of these rectangles and add them together. And then when I is 2, I go across all of these rectangles and add them together. So forth and so on, right? I get all those rectangular prisms, add them all together, and that's going to give us this double sum. So each value here, I from 1 to m, corresponds to a row, and each of these is one of the rectangles in that row. So this will sum up a whole row, and this tells us to sum up all of the rows together. So hopefully that's pretty clear. So then we define volume intuitively as the limit of these sums as the size of our rectangles goes to 0. All right, and therefore, the definition of the double integral of f over the rectangle R is the double integral over the region of f of x, y, dA equals the limit of these double sums, provided that this limit exists. So we call a function in R2 integrable if this limit exists. And the key fact here is that all continuous functions are integrable. So if we already know a function is continuous, then we don't have to worry about it. We know that this limit exists, and we can find a value for the double integral. Now, additionally, if f is bounded on a rectangle R and continuous on R except for a finite number of curves, then f is also integrable. So why is this okay? Well, if f is bounded and there are discontinuities on finite numbers of curves, an individual curve has no width, so it has no area. So it doesn't cause you a problem. And since f is bounded, you don't have any sort of infinite limit that can cause you some real issues with the volume. All right, so let's go ahead and kind of tackle a problem here. If R is equal to the set of points x, y, where x is between -1 and 1, and y is between -2 and 2, evaluate the integral. So this is the double integral over R of the square root of 1 minus x squared with respect to area. Okay, well, we don't really have a good process for this yet, but if we understand the interpretation of the problem, then we know what this is asking us for is the volume of the figure generated by the surface z equals the square root of 1 minus x squared, where x is between -1 and 1, and y is between -2 and 2. So let's try to draw this. Well, if z equals the square root, then z squared equals 1 minus x squared, or x squared plus z squared equals 1, under the condition that z is greater than or equal to 0. Okay, so z is greater than or equal to 0 here. So what does this look like? X squared plus z squared equals 1. That's a circle on the xz axis. But since z is greater than or equal to 0, or greater than or equal to 0, then it's not really a circle, it's a semicircle. So it's the circle, the top half of the circle on the x and z plane. But we're not just going from x equals -1 to 1, we're also going from y equals -2 to 2. And this is not a perfect drawing, but hopefully it's good enough to convey the idea. Wow, that got really, really sloppy there. Let's try that again. that's terrible. Okay, I need to stop wasting time drawing this picture because I'm not an artist. But hopefully you recognize that if this is a semicircle, and we're just taking this semicircle and dragging it from -2 to 2 along the y-axis, then what we get is half of a cylinder. So this is equal to the area of a half cylinder, which is what? Well, in this case, the base of the cylinder has radius 1. So pi times 1 squared, that's the area of the base, times the length of the cylinder, which is 4. So this is just 4 pi. So even if you're a terrible artist like me, you can still draw a picture good enough, hopefully, to interpret this problem and figure out what it's asking you to do. All right, so let's go ahead and move along. So I'm just going to mention this in passing, but keep in mind that the midpoint rule for double integrals, the midpoint rule still exists, just like for regular single integrals. And we can still use this approximation method here. It's the same basic idea. So if we let the partition of R be regular such that all subrectangles have the same area, delta A, and the coordinates of each sample point, x sub I bar, y sub j bar, correspond to the midpoints of the subintervals respectively, then that should say approximately there we go. So then the double integral over R of f of x, y, dA is approximately equal to the double sum of f x sub I bar, y sub j bar times delta A. Now, I'm not going to do any examples of this here, but just keep in mind that the process is pretty similar to this process you would have used in Calculus 1 or Calc 2 even. Okay, so now let's talk about iterated integrals. So it's important that we have a more consistent approach to being able to compute these integrals. We're not always going to get something as nice as a half cylinder to work with. And frankly, midpoint rule approximation, while extremely valuable, is also dense and time consuming, and it's much better if we have a direct computation method that we can use at least a lot of the time. So that's where the following Fubini's theorem comes into play. If f is continuous on the rectangle, where x is between a and b and y is between c and d, then the double integral over R of f of x, y, dA can be represented as the integral from a to b of the integral from c to d of f of x, y, dy, dx, or the integral from c to d of the integral from a to b of f of x, y, dx, dy. In other words, you can integrate with respect to y first, then x, or x first, then y, and you'll get the same thing as long as you make sure to adjust your bounds accordingly. Your inside integral should always be the bounds that correspond to that variable that you're integrating first. So more generally, we can say that this is true as long as f is bounded on R and f is discontinuous on only a finite number of smooth curves, and the iterated integrals exist. So we've got some pictures here, but they're not really going to give you the perfect idea of what they're trying to represent, but hopefully it's it's helpful for looking at in your notes. But let's actually take a look at a little applet to display this better. So if we take a look here, we've got some fixed x value, and when we integrate for that fixed x value, what do we get? We get this integral over y. So here we're actually integrating along the y-axis, and we get an area that's based on that integral with respect to y. So then what are we doing? So we get this little sliver that provides an integral, and then we take and move the x value here. And that area changes, and we sum up all of them little areas multiplied by their little widths, their little sliver of width. So the movement of this surface here, this like plane segment under here, is the integration of your second variable. So your first variable gives you the area function, like here at any fixed x value. And then your second integration over the x takes all those areas times their little widths and sums them all up and gives you the total volume. And likewise, if we did the same thing but with the cross section here, we'll get the same volume, except here what happens first is your area is based on integrating with respect to x first, and then taking that area result and integrating it across the rest of the surface to generate the volume. So hopefully that makes some sense and helps you picture this idea a little bit better. Okay, so moving on, let's go ahead and calculate a double integral. So we've got the double integral over r of x cosine of xy dA, where r equals the interval over x from 0 to 1, and the interval over y from 0 to pi over 4. Now keep in mind, we could do this two different ways. So we could integrate with respect to x first, in which case my bounds here would need to be 0 to 1 and 0 to pi over 4. Or we could integrate with respect to y first. Now, it won't always make a significant difference in the difficulty of the integral, but sometimes it can make a huge difference. So it's helpful to think about both possibilities and see which one you think would be easier to compute if you can think ahead a step or two. So here, if I'm integrating with respect to y, x is a constant, and so I would just be integrating this basic cosine function, so that would be pretty easy. But then I would have to integrate with respect to x, so I'd still have like x times cosine, a sine of a function of x, something like that. Now here, if I'm integrating with respect to x first, I've got to deal with having this product of x times cosine of xy. So that's a little bit complicated. Got to use integration by parts there. And then once I integrate that, I'm going to have something uv minus integral of v du. So then I'm going to have to integrate all of that with respect to y. And it seems like I'll have a bigger, maybe somewhat more complicated expression, but all of my x's will be replaced with constants at that point, so it might not be too bad. So it's actually a little bit hard for me to pick which one I think would be worst. So I'm just going to go ahead and go with the one on the left here, and we'll ignore the approach on the right. So what do we get here? Well, I need to use integration by parts. So for my inside integral, I want u to be x, du to be 1 dx, dv to be cosine of xy dx, and then v is the integral of this. Now, I technically need a substitution rule here, but that substitution is going to be like w equals xy, so dw equals y dx, so I divide by y. So I end up with just sine of xy divided by y. So uv, so first we've got the integral from 0 to pi over 4, that hasn't gone away, of uv, that's x times sine of xy over y minus the integral of v du evaluated from 0 to 1. And then once I evaluate that, I've got to integrate with respect to y. So just thinking ahead here, what do I see? Well, when I integrate this, I'm going to get like negative cosine of xy over y. So I'm going to have over y squared here. And then if I have to integrate that with respect to y, that's going to be very, very challenging. So this is a perfect example of like, hey, I got to step in here. This looks super hard once I get to that point. So let's try the other way. And this is the key thing to learn about this particular material, which is that when you're doing these double integrals, there is no rule that will tell you which one to use first, but the power of that theorem is that you can pick which one you want to use first. So if it doesn't go so well for you to try to integrate it with respect to one variable before the other, try it the other way around and see if you get something a lot nicer. So now in this case, let's see what we get. Well, x is a constant here, so we're just integrating cosine. So that's sine of xy, and I would have needed to do u substitution, but I would have gotten that I just had to divide by y here. And then I need to evaluate this from 0 to pi over 4 dx. Now, remember, this first variable we're integrating with respect to is y. So when we evaluate at pi over 4 and 0, we need to keep in mind that this is y equals pi over 4 and y equals 0. So this gives us x times sine of pi over 4 times x divided by pi over 4. Oops, I made a little mistake. That should have been divided by y. That should have been divided by x, because x is my constant, y is my variable. So that should have been over x here. Minus this evaluated at 0 for y, but sine of 0 is 0. So that whole thing will be 0. And we got really lucky, which is that x over x is going to cancel here. So that's going to leave us with the much simpler integral, the integral from 0 to 1 of sine of pi over 4x. Now again, this would require a substitution rule, but it's easy enough. So we get cosine of pi over 4x divided by that constant, pi over 4. And evaluated from 0 to 1. So this becomes negative cosine of pi over 4 over pi over 4 minus cosine of 0 over pi over 4. So this is negative root 2 over 2 divided by pi over 4 minus 1 divided by pi over 4. Now division is multiplication by the reciprocal, so I can kind of clean these up a little bit and make this negative 4 root 2 over 2 pi minus 4 over pi. 4 over 2 is 2, and so this is negative 2 root 2 minus 4 all over pi. Okay, so that's it for that example, and hopefully this was a good illustration of this idea that you have to be willing to adjust which way you're integrating with respect to in order to find the easiest approach in general. Okay, so let's take a look at this next one. The integral from 1 to 3 of the integral from 1 to 5 of ln of y over xy with respect to y first, and then dx. Okay, so first we'll have to deal with that interior integral. So here I've got to do a u substitution. So u is going to be equal to ln of y. So du equals dy over y. Ln of 1 is 0, and ln of 5 is just ln of 5. So that changes our bounds here for this integral from 0 to ln of 5. And then we've got u du over x dx. Now when I integrate this with respect to u, I'm going to get u squared over 2x evaluated from 0 to ln of 5, and then integrated with respect to x. Now when I evaluate u at these bounds, what do I get? I get ln of 5 squared divided by 2x minus 0. And now I integrate this with respect to x. So ln of 5 and 2 are constants, so I'll pull those out. And the integral of 1 over x is ln of the absolute value of x, evaluated from 1 to 3. Ln of 3 is 3, and ln of 1 is 0, so this gives me ln of 5 squared over 2 times ln of 3 minus 0. All right, so that's it for that example. Just keep in mind with these double integrals that it's basically the same process that you use for regular integration. You just, with that, whichever variable you're integrating with respect to, you just need to keep in mind that the other variable needs to be treated as a constant during that step. So other than that, it's pretty much the same old thing, but twice in a row. Okay, so just a couple quick properties and then we'll wrap this up. Just like for regular integrals, the double integral of a sum of two functions is equal to the sum of each integral individually. The double integral of a constant times a function is equal to the constant times the double integral of that function. And if a function is strictly greater than or equal to another function for all x and y in a rectangle, then the first function's integral over that rectangle is going to be greater than or equal to the second function's integral over that rectangle as well. And that's it for 12.1 double integrals over rectangles. Thank you for watching.